Alrighty, so let's hit possibly what will become one of the base starting blocks for where we're going to go with a lot of our trig. In trig, we actually use our understanding of the primary trig functions to determine a lot of things related to these right angles. Now we are going to be sticking primarily to these right angles, but obviously you're not going to really see a lot of it. First one is, well, the first thing that we're going to do is we're going to talk about a lot of things in relation to what we had done in Pre-Calc 20. So obviously, first thing that we're going to talk about is cast. Now, cast is just a quick little way of telling us which ratio is going to be positive in each quadrant. And the way that we had learned it is that in each of our quadrants, 1, 2, 3, and 4, certain ratios are positive. For example, in quadrant 1, all of them are positive. In quadrant number 3, tangent is positive. In quadrant 4, only the cosine is positive. And in quadrant 2, the sine is positive. So our cast comes from just those first letters of each of those things. C-A-S-T, yes, it doesn't fully make sense that we start down in quadrant 4, but it's just one way that it's the easiest way to really remember instead of trying to just go with astica. Not really the easiest thing to memorize. So the other thing that we had done in Pre-Calc 20 is, under my guidance, we had learned the hand rule. Now, when I learned learned this entire table thingy in school, we had to do it. We had to just memorize the entire table. When I learned in university, and there was actually kind of a way of quickly doing it, it made things so much faster. So we'll talk about this hand rule in just a second. But if you make a hand, your first digit is 0, the next one's 30, then 45, then 60, then 90. But since we learned section 1 where we learned about radians, we also have to talk about what are these degrees in radians. So just as a quick little review, our radians, the amount of radii that are around a circle. Of course, tying in that one entire pi is 180 degrees is probably going to be the key thing to remember and know. So that key bit of information, since we know that pi radians, again, reminder, you don't need to have that r, is 180 degrees. 0 degrees would obviously be 0 radians. 0 degrees is 0 radians. But if you look at proportionally, 30 degrees, how much is 30 out of 180? Well, it's 1/6. So if 180 degrees is 1 pi, 30 degrees would have to be 1/6 of this size. Now we're not going to use to the decimal, we're going to go to the exact, which means we're going to call it 1/6 of a pi. Either pi over 6 or 1/6 pi. It's just usually a lot nicer to write pi over 6. If we do the same kind of bit for 45, 45 out of 180 is a quarter. So 45 degrees is a quarter of pi. 60 degrees, in the same kind of fashion, is 1/3 of a pi. And 90 degrees, which is exactly half, would obviously be 1/2 pi. So it doesn't really matter whether you write it as 1/6 or pi over 6. You write it as 1/4 pi or pi over 4. It's still going to fit the same kind of bit. But what you need to know is that, yeah, 0 degrees is 0. 30 degrees is pi over 6 or 1/6 of pi. 45 is 1/4 pi. 60 is 1/3 of a pi. And 90 is 1/2 pi. Which means instead of just using our hand rule with 0, 30, 45, 60, and 90, we can also use these as these radian measures. Yes, I can already hear the groans. Alrighty. So to perform the hand rule, you take the square root of the number of fingers to your left of your finger and divide it by 2. Now, that works for sine going this way. So meaning, divided by 2. In relation to our 0, there are no digits to the left. So the sine of 0, or 0 degrees, or 0 radians, is the square root of 0 over 2. The square root of 0 is 0, divided by 2, which means it is 0, no matter what, 0. The sine of 30 degrees, or the sine of pi over 6, which is the same thing. How many digits are to the left of your 30? There's only 1. So it is the square root of 1 over 2. Square root of 1 is 1. So meaning the sine of 30, or the sine of pi over 6, is 1/2. 45, how many digits are to the left? There's 1, 2. This one is just quick. Root 2 over 2. Boom. 60. There are 1, 2, 3 digits to the left. So it is the square root of 3 over 2. For 90 degrees, or pi over 2, how many digits to the left? There are 4 digits. So the square root of 4 over 2, the square root of 4 is 2. And 2 divided by 2 is 1. Cosine is read directly backwards. So instead of reading to the left, we're going to read to the right. Now the angle measures in either degrees or radians are stay the exact same. The only difference is that you're just reading to the right. So how many are to the right of this 90? Well, there's 0. Square root of 0 is 0. The faster way of knowing it, though, as soon as you've done your sine, your cosine is just each of these numbers backwards. Yes, the sine and cosine of pi over 4, or 45 degrees, are both root 2 over 2. For tangent, and this is actually one thing that we're going to talk about in identities, it is actually just the sine divided by the cosine. So we can actually do these ones really quickly, or some of them really quickly. Some of them take a little bit extra work. For example, 0 divided by 1 is 0. I'm going to skip this one for a second. Root 2 over 2 divided by root 2 over 2. Anything divided by itself is 1. 1 divided by 0 is undefined. Or if you're really fancy, absolutely, it is a vertical asymptote. And we don't have to really need to know that too much. We're not going to be doing too many undefineds, but as long as you know that it is 1 divided by 0, which is undefined, we'll talk about this tangent having vertical asymptotes in a later unit. Alrighty, this is probably the fastest one to do. I'm actually going to do that over here. Root 3 over 2 divided by 1 over 2. So in order to divide fractions, it's root 3 over 2 multiplied by 2 over 1. It just means 2's cancel off, and it'd be 3 over, or root 3 over 1, which is just root 3. If I do this one, 1/2 divided by root 3 over 2. is going to be slightly different because we're going to do some skills that we had talked about last year in Pre-Calc 20. You flip, you multiply, you cancel off the 2's, but then we still have a 1 over root 3. So the skill that we had done in Pre-Calc 20 is rationalizing our denominator, which means multiplying both the top and bottom by that radical that's in our denominator. And 1 times root 3 is root 3. Root 3 times root 3 is square root of 9. But what's the square root of 9? It's just 3. So the tangent of 30 degrees, or the tangent of pi over 6, is root 3 over 3. And just the same as last year, either you can memorize how to do this, or really the fast, honest and true way, it's kind of just memorizing this root 3 over 3 and this root 3. As long as you can apply your hand rule, there's sine. Cosine is the same backwards. 0, 1 in your 45, undefined in your 90, and really you're set. So this is essentially the stuff that we had done last year, Pre-Calc 20. Obviously adding in that little bit of radian stuff that we had talked about in section 1. Now we're going to talk about a little bit more stuff that's actually new. And then we're actually going to go back to some kind of skills that we had done in Pre-Calc 20, just we're going to apply our radians. So in trig, we're not limited to just our primary trig ratios of sine, cosine, and tangent. They are the only ones on our calculator though, so we can't do anything special or anything other special than that. But there are also what are known as reciprocal identities. They are called the cosecant, the secant, and the cotangent. Apparently I'm missing a few things that I need to fix up. Sorry for not having some equal signs. Anyways, the reciprocal, or sine has a reciprocal identity. And again, we'll also talk about this a little bit later on, just like when we talk about the tangent. The reciprocal of sine is, instead of having sine, we have what's known as the cosecant. So the pairing is sine and cosecant. The abbreviation for cosecant is a CSC. So if I talk about the cosecant is actually 1 over the sine of whatever angle we're talking about. So sine is actually 1 over cosecant, and cosecant is 1 over sine. Cosine is paired with secant. Cosine, instead of writing cosine, can also be written as 1 over secant. And the abbreviation for secant is actually SEC. Still need our theta though. So SEC is the same as 1 over the cosine of whatever our angle is. Tangent, obviously, really works out nicely. Tangent's pair is cotangent. The abbreviation for cotangent is COT. So cotangent is actually 1 over tangent theta. How do you keep that straight? Well, every single one of these pairs have a co to it. Sine has cosecant, cosine has secant, and tangent has cotangent. Absolutely would make more sense if our primary ratios were sine, secant, and tangent. Therefore, the reciprocal identities would be cosecant, cosine, and cotangent. So that literally this reciprocal of sine could be cosine, the reciprocal of secant could be cosecant. But unfortunately, that is one thing that I haven't actually done any research into as to why. So I apologize. We'll talk about some transformations between sine and cosine, but why they didn't just have these sine and cosine as the reciprocals, and secant and cosecant as reciprocals, I don't know. So that's something that I will for sure one of these days remember to actually search into it, but that's not right now. Okay. Cast, applying our radians into our angles, relearning our hand rule with our chart. Okay, one thing you might notice if you do talk to friends or if you're not in my class and you're actually watching this video, this entire table can also be known as what are called special triangles. Some teachers do treat it as or call it this way. I just find that this table works out a lot nicer, especially with our hand rule. Long story short, there's triangles with like a 30 and a 60 degree, and then the ratios are obviously just your SOHCAHTOA stuff. It's really faster to do it this way than trying to memorize. Yes, it is only 2 triangles, but it's so much easier to just have this stuff memorized. At least in my perspective. If you want to learn it, absolutely just ask me and I will fully teach it to you. Alrighty, our next page. Okay, oh, and obviously what are called the reciprocals. Now, trigonometry has been using the idea of using right triangles to help solve for side lengths and angles. This can be extended to a circle and bisecting it vertically and horizontally using the trapezioid plane. Now, I would absolutely love to try and like animate this. That's a way longer project that should come out pretty soon. But again, I apologize, not right now. So this looks like a very long and convoluted way of writing a circle, but it's actually quite elegant in the way that it's done, as well as all the extra information that's on here. For example, this is what's known as the unit circle. It's called this because the radius of the circle is 1 unit. Each of these coordinates around the circle are exact values using the reference angles derived from our hand rule and through cast. Each coordinate xy is written exactly as cosine theta comma sine theta. This is basically making the connection that cosine is actually our x values and sine is our y values. So that's kind of something that doesn't get applied into some other stuff. We don't really touch on this part too much, but what I am going to tie into is this. So each and every single one of these coordinates are written as, again, cosine comma sine. If we look at 30 degrees, and if we use our hand rule, or we just go back to our table, for 30 degrees, our cosine value is pi over 3, or root 3 over 2, and our sine of 30 is 1/2. On this unit circle, that's exactly what's displayed. Same time knowing that 30 degrees is pi over 6. So it's actually connecting our angle, our radian, our cosine, and our sine. Tangent, you yes, absolutely still have to derive by taking this one and dividing it by this. So we still have to do that where it's 1 divided by 2. Or you use your hand. The sine and cosine of 45 degrees, or sine and cosine of pi over 4, is root 2 over 2. The cosine of 60 degrees is 1/2. The sine of 60 is root 3 over 2, or pi over 3. The sine of 0 is 0. The cosine of 0 is 1. The cosine of 0, cosine of 90 degrees, or pi over 2, is 0, and the sine is 1. But that only deals with our first quadrant. The quadrant where all of our ratios are positive. And tying back to last year with our pre-calc 20, we were talking about, again, that reference angle. That reference angle. And our reference angle is always the angle that's made between the x-axis and that terminal arm. Doesn't matter where it is, it's always going to be that x-axis. Now I'm actually going to talk about that reference angle when we go into quadrant 2. In quadrant 2, 150 degrees has a reference angle of 30. But our sine of 30 is 1/2. Absolutely it is. Because again, all of our coordinates are still go cosine comma sine. Our cosine of 30, though, is √3/2. So why is this negative? Because in quadrant 2, the only thing that is positive is the sine ratio. I'll come back to the radian measures in just a second, but you'll see that every single time. For 135, our reference angle is 45. Both values should be √2/2, but only the cosine is negative. For 120, our reference angle is 60 degrees. Cosine is 1/2, and obviously it's negative in quadrant 2. Our sine is √3/2. I'm going to go to the reference angle is 60 degrees in here. So that is a 60-degree angle there, or pi/3. And we'll talk about that in just a second. But you'll notice in every single one of these quadrants, doesn't matter whether we're in quadrant 1, 2, 3, or 4, these coordinates with these reference angles maintain the exact same locations, just depending on positivity and negativity. For 30 degrees, which means 30, 150, 210, and 330 all have the same reference angle, they are always going to be √3/2, 1/2, √3/2, 1/2, √3/2, 1/2, √3/2, 1/2. Every single one of our points for a 45-degree reference angle, which means 45, 135, 225, and 315, all have √2/2 as both locations, but it depends on whether our cosine, our sine, tangent, or all of them are positive. And last but not least, obviously, our 60-degree reference angle. With the idea of having this unit circle, we also have these points, which are actually really nice to point. Sorry, that was a really bad pun. It's really easy to point out that using that unit circle, this would be the point 1, 0. This is 0, 1, -1, 0, and obviously 0, -1. Now, I did say that I would come back to these radian measures. You do not have to completely convert every single one of our degrees into radians by hand if you know your fractions. So if we go by hand, 120 degrees and 180, 120. And 180 are both divisible by 60. 2 and 3, 2/3 of a pi. 135 degrees is 3/4 of 180. 150 is 5/6 of 180. But that kind of comes down to the end of there. Unless you do get really good at fractions, it gets a little more difficult to try and convert 210 into 7 pi/6. Unless, again, you know your smaller fractions. And we did that. 30 degrees is pi/6. 45 degrees is pi/4. 60 degrees is pi over 3. So what's our connection between 60 and 120? 60 and 120, 120 is twice the size of 60. 135 is 3 times the size of 45. 225 is 5 times the size of 45. So if you start looking at a lot of the connections between each and every single one of these smaller fractions to these bigger exact values for our unit circle, and using that hand rule, these fractions actually get a lot easier. And we are going to practice these ones quite a bit. Apparently I like going in a circle. Okay, sorry. If you can memorize this, great. But all you're going to need is really this and these. And I'm going to show you right now. We're going to use this unit circle to determine the exact value of the sine of 5 pi over 4, which means we're looking for 5/4 of a pi. So where are we going to look for a quarter? Well, again, if we're looking at our table, we're looking for essentially that 1/4 pi. And a 1/4 pi is 45 degrees. So if we use our sine, or yeah, if we use our hand rule, the sine of 45 is √2/2. But we're not looking at the sine of 45. The sine of 45 is in quadrant 1. 5 pi over 4 is a little bit more. So let's look at this really quickly. 5/4. 5/4 is 1.25. In other words, that's 1.25 pies. If we look at our entire circle, this is 1 pi, this is 2 pies, so this would be obviously a half, this is 1, this is 1.5, this is either 0 pies or 2 pies. 1.25 would have to be down in this quadrant, down in quadrant 3. Actually, I'm going to write that here. So since it's quadrant 3, this number, since it's sine, and it's, actually I'm going to change my color, CAST, it's going to have to be, tangent is the only thing positive, sine is for sure negative. Of course, if you want to get, I'm going through all the things without having to go back and forth with pages. If you need to get a little more comfortable with it, and you will. It just takes practice. It takes time. Absolutely. Let's go to 5 pi over 4 on our unit circle. 5 pi over 4 is right here, and the sine value is that negative √2/2. Again, keep in mind it is sine or cosine, then sine, xy. The cosine of 5 pi over 6. So 5 pi over 6 is a little bit difficult. We're going to look for these sixths. Well, which of our stuff deals with sixths? Are 30 degrees. Sorry, I'm just going to actually change that color just to be consistent on my examples. Cosine of pi over 6, so we're dealing with the cosine of 30. The cosine of 30 is √3/2. But 5/6 is not a full pi. It's definitely more than half, but it's not a full. which means we are in quadrant 2 here. 5/6, negative root 3 over 2. So let's go to our unit circle to take a look at this. 5 pi over 6 is right here. Our cosine is negative root 3 over 2. I made this entire page of these. Yes, I did. Perfect. So lots more examples. Tangent, 3 pi over 2. Okay, that's exactly 1.5. That is exactly 1.5. So we're dealing with down here. And our tangent is, again, the sine divided by the cosine. Well, what's our reference angle down here? So actually, now I'm going to put it in radians, then I'm going to put it in degrees. Sine, then our cosine. Pi over 2. Or in other words, sine of 90 and the cosine of 90. The sine of 90 is 1. The cosine of 90 is 0. Now, we also have to keep in mind what our stuff is here. In between here and here, the only thing that's positive would be tangent and cosine. The sine would definitely have to be negative. So I'm just going to keep that in mind. At the same time, we also do know that the coordinates there are 0, negative 1. So I'm just going to come back to this unit circle just to say, yeah, the coordinate at 3 pi over 2 is 0, negative 1. So really, negative 1 divided by 0 is undefined. That's all there is to it. Right. Let's go for some more. Cosine of 5 pi over 3. Similarly, we're looking for those thirds. Pi over 3. Well, 1/3 of a pi, which angle measure is 1/3 of 180? That is our number 60. So the cosine of 60 is 1/2. Cosine of pi over 3 is 1/2. So let's look at 5/3. 5/3 is 1.6 repeated, which means we are down in quadrant. Sorry, actually, just for notes, this should be in between quadrant 3 to quadrant 4. Obviously, because it's undefined, we didn't really need to know that too much, but it's just kind of one of those things. 1.6 would therefore be in quadrant 4. And in quadrant 4, the only thing positive is cosine. So this one would have to be positive. Again, as I've said many times and many years before, you don't have to write a positive. But let's keep on going. Sine of 7 pi over 6. So what we're looking for are the sixths. Not the Jedi, just the sixths. Oh, I'm sorry, that one was just too perfect. Sine of 30 is definitely 1/2. 7 over 6 is just over 1, which means we are in quadrant 3. Meaning, only thing positive in quadrant 3 is tangent. Does it have to be negative? All right, let's go back and check these two. 5 pi over 3 and 7 pi over 6. 5 pi over 3 right here, our cosine is a positive 1/2, and a 7 pi over 6 is a negative 1/2 for the cosine and then the sine. The tangent of 2 pi over 3. So the tangent of 2 pi over 3 does still mean the sine of 2 pi over 3 over the cosine of 2 pi over 3. But since we're dealing with the thirds, we're going to look at what is the sine of pi over 3 and the cosine of pi over 3. Thirds, 60s. Okay. So we're looking for the sine of 60 divided by the cosine of 60. The sine of 60 is root 3 over 2. But we have to divide it by the cosine of 60, which is 1 over 2. So flip and multiply. Root 3 over 2 multiplied by 2 over 1. Some 2's cancel off. We're left with a root 3. Of course, if you know that the tangent, very similarly, the tangent of 60 is root 3, you're set. The last thing we need to do is 2/3 is 0.6 repeated, which means we're in between this 1/2. The only thing positive is sine, which means it would have to be a negative. Tangent is not on your unit circle. So by going through this method, this tangent of 2 pi over 3, 2 pi over 3 is our sine divided by the cosine. Or once again, tangent of that pi over 3, tangent of 60, is root 3. So now that we got a little bit of a handle on this, we're doing pretty good. I'm actually just gonna, this means that we're in quadrant 2, so that's why we're dealing with the negative. I'm gonna cheat very slightly. 3 pi over 2 is right here. I know that the cosine of that 3 pi over 2 is 0. Actually, sorry. Where did I get that? 3 pi over 2 is using the halves. Or, in other words, cosine of 90. But 3 pi over 2 is exactly 1.5. So down here, our cosine is 0. And obviously the number 0 doesn't need a positive, nor does it need a negative. So now that we've gotten a handle of it, I'm going to throw a wrench into your game. Everything before, we just dealt with sine and cosine and tangent. Yes, just like in pre-calc 20, I asked you a lot of these things before, just only with degrees. They actually look exactly like these. Actually, this one was literally taken straight from pre-calc 20 examples, but that's beside the point. Just like on the front page, we had talked about those reciprocal identities. Secant is not one of our is not one of our values on here. We have our cosine and sine. We can derive tangent, which means we should also be able to derive secant. Secant is the reciprocal of cosine. So instead of writing secant, what we're doing is we're actually taking 1 over the cosine of 5 pi over 6. Now I'm going to do a whole bunch of work here. This is 1. We're dealing with the sixths. Cosine of pi over 6, which means 30. So 1 divided by the cosine of 30, well, the cosine of 30. Let's see, by using my hand rule, As to the right, it's root 3 over 2. So 1 multiplied by 2 over root 3 would obviously just be 2 over root 3. But I don't like those. I like doing our stuff that we did in pre-calc 20, where we rationalize it. Yes, I already do know that your textbook will have things. You don't have to write this, but I know for a fact that your textbook will have things that are written like this. It is just root 2 over 2. Because when you rationalize it, that's root 2. 1 times root 2 is root 2. Root 2 times root 2 is root square root of 4, which is 2. Similarly, 2 times root 3 is 2 root 3. Root 3 times root 3 is the square root of 9. Square root of 9 is 3. So we just dealt with secant of 5 pi over 6. 5 pi over 6 is in quadrant 2, and the only thing positive is sine. Cosine and secant are reciprocals, which I didn't talk about before. But if cosine is positive here, secant is positive here. If tangent is positive here, cotangent is positive here. If sine is positive here, cosecant is positive here. I sure hope that I said that right. Cosine and secant, tangent and cotangent, sine and cosecant. The only things positive here would be sine and cosecant. Secant is definitely not, which means this answer would be 2 root 3 or negative 2 root 3 over 3. Now, since we dealt with that, let's do another one. Secant 315. Okay, now we're getting away from the radians. We're getting back into some degrees. This would be the 1 over the cosine of 315. But 315 is not really a nice number to work with. 45 is a nice number to work with. So 1 over cosine of 45. 1 divided by the cosine of 45. 1 divided by root 2 over 2, which means it literally just becomes a 2 over root 2. And then we rationalize. Multiply top and bottom by the square root of 2. We get 2 root 2 over 2. The 2's even cancel off. We get an answer of root 2, and 315 is in quadrant 4. Quadrant 4, cosine is the only thing positive, and since secant is the reciprocal of cosine, secant is also positive in quadrant 4. Okay. 2 last ones on this. Then some more stuff. Yeah, this is a very long section. It's a lot of information. Cotangent of 270. 270 means 90. So cotangent, being the reciprocal of tangent, which means it's 1 over the tangent of 90. But the tangent of 90 is undefined. Or it's 1 divided by something that is undefined. 1 over 0 is undefined. How do you divide by a fraction? You flip and multiply, which means that this becomes 1 multiplied by 0 over 1, which means our answer is actually 0. So that's a little bit of a trick to that one. And then we'll talk about pre-calc 20. 225 is 45. So the sine of a 45-degree angle is root 2 over 2. 225 is in quadrant 3. Only tangent is positive in quadrant 3. So absolutely, we started with hard ones. And through lots of practice, hopefully this relatively is okay. Alrighty, continue on with our unit circle. We're also going to talk about some more circles, just to kind of tack it in. The key aspect to a unit circle is that the radius is 1 unit, which means the equation x squared plus y squared equaling 1 is actually the equation of this circle. What it does is it helps us to derive the equation of any circle at the origin, and all of our circles will always be at the origin. Back in the previous curriculum with C30, with Math C30, we actually did do circles that were not based at the origin, just dealt with some transformations. Actually, it wasn't too bad to deal with it, but there's a lot of extra stuff to it. Long story short, the equation will always be x squared plus y squared equals the radius squared. R is the radius. So if we want to determine the equation of a circle at the origin with diameter 8, this circle at the origin is just some wording, just so that we're not dealing with, oh, what about if our circle is at the point 5, 5? It's like, no, we're not dealing with that. We're just dealing with at the origin. So x squared plus y squared equals the radius squared. If our diameter is 8, our radius is 4. So 4 squared. X squared plus y squared, 16. Done. Now the length, so that's kind of just one little throwaway stuff. I know that'll have some in your unit assignment bit. You'll have some practice questions. I don't think I even have, I might have one on your final. I'll have to double check, but yeah. New little bit, the length of an arc of a circle is calculated by the formula A equals pi r, where A is the arc length, so A, and r is the radius, and theta is the interior angle measured in radians. It says S, but it should say A. What does lead us to one fantastic realization. Is the idea of one full circle. Within one full circle, we have 360 degrees. Or if we dealt with it as radians, it's 2 pi radians. So if we're going to use the formula, A equals pi r, sorry, not pi r, theta r. I probably didn't say that when I actually read the formula the first time. Theta r. Our theta for a full circle is 2 pi. R is whatever the radius of that circle is. This is the formula for the circumference of a circle. So there's just a little tidbit of information for you. It's kind of, hey, I think it's fun. All right, we'll do 3 examples really quick here. Determine the length of an arc of a circle shown below. So we want to find out this S. Really, it's asking for what the arc is. So arc is theta. So our interior angle, again, it has to be measured in radians times by radius. So our theta is 2.2, our radius is 12, that arc length 26.4, and our unit is actually centimeters. So this really quick little bit of information. Yes, of course, I'm going to make it a little bit harder. Determine the radian measure of central angle in the circle shown. So it says that our arc length here is 8 centimeters. We don't know what that interior angle is, but we do know what the radius is. It's 24 millimeters. But this is 8 centimeters. We don't want to try and deal with two different types of units, but we do know that there are 10 millimeters in 1 centimeter. So instead of 24 millimeters, that's 2.4 centimeters. So to quickly solve for theta, we just divide by the 2.4. Quick, easy, painless. Theta would be 3.3 radians. Rosemary is taking a course in industrial engineering. For an assignment, she has designed the interface of a DVD player. In her plan, she includes a decorative arc below the on-off button. So your on-off button, again, it's just that one that looks like that. So there's some kind of decorative arc underneath, usually lit with some LEDs or something like that. In our plan, the central arc of the angle is 130 degrees. In a circle, the radius is 6.7 millimeters. We want to determine the length of the arc to the nearest tenth of a millimeter. Okay, so everything's millimeters, so we're really set to go. So arc length is theta multiplied by our radius. So arc length, our theta multiplied by our radius. So our radius is 6.7. And our theta is not 130. Theta has to be measured in radians. 130 degrees is not in radians. So in order for us to do this question, we actually have to convert that 130 degrees into radians first. That's why we did this kind of stuff in our first little section. Now I know that they're both divisible by 10, which means that this would actually be 13 pi over 18. And all we have to do is type that straight into our calculator. 13 pi divided by 18 times by the 6.7. And the arc length would come out as 15.2 millimeters. If that actually looks like an M. So you can guarantee that I'm going to have a question in degrees asking for the arc length, and someone will for sure try and give me the answer of 871, which is just 130 times 6.7. So don't get caught. Alrighty, last example. Yeah. Really quick here. Determine coordinates of all points in the unit circle that satisfy these conditions. Draw a diagram. Long story. We still have that unit circle. We have some points. We have the point negative 5, 8, y, and x, 5, 8, 5, 13, x, comma, 5 13ths. Except this point is in quadrant 2. So let's see what that means. We know a few things. One thing we know is that our circles, every single one of our circles, have the equation x squared plus y squared equals the radius squared. One other thing that we can see from this question is that we are actually dealing with a unit circle. If we're dealing with a unit circle, that means our radius is 1. So all we have to do is x squared plus y squared equals 1 squared. Negative 5/8 squared plus y squared equals 1 squared. 25/64 plus y squared equals 1. I need to try and get my y squared by itself, so I'm going to need to actually get a common denominator over here right away. And I'm going to subtract that 25/64 over. Which comes out as, should be 39/64. Doing my math right? Yep. And then we square root. But here's the trick. Square root of the top is just 39. Actually, it's not, but we'll get to that in just a second. The square root of the bottom of 64 is 8. We take the square root, it has to be the positive and the negative. Because we're not dealing with just the situation with our unit circle. We're not dealing with just the point where negative 5/8 as our x and 39, square root of 39 over 8 being there. We're also dealing with the point that negative 5/8 could also be the point negative root 39 over 8. So we could potentially have two coordinates. Negative 5/8, negative 5/8, root 39 over 8, and negative root 39 over 8 as these coordinates. Last one, not as intense. Actually, this one I know will actually come out a lot nicer. X squared plus 5/13 squared equals that 1 squared still. X squared plus 25, 1/69. I know that I'm going to have to subtract some stuff over, so I'm just going to go immediately to making that common denominator. 169 over 169, because that is just 1. And then I'm going to subtract that over. Subtract the 25 over 169. We have 144 over 169. Take our root. And x would be positive or negative 12/13. But since we're only dealing with quadrant 2, we only care on our unit circle in quadrant 2. We only care about whatever this one is, which means that we only care about the positive answer. It should be 5. Yeah, 5/13. Alrighty, that's it. Lots of stuff. Have some fun.